Okay, so for this notes packet, we will actually spend 2 days and you will have 2 homework assignments. One day we'll be talking about vertical asymptotes, and one day we'll be talking about horizontal asymptotes. So, essential questions for the first day. What's the calculus limit definition of a vertical asymptote? And I'm just going to abbreviate. And then when evaluating a limit by plugging in, how do you know you're dealing with a vertical asymptote? How do you know you're dealing with a vertical asymptote? Just as a heads up, we will use this same starter page to add our essential questions for the second day, and you will actually have 3 of those on the second day. So this is a section, since we're spending 2 days on it, you will have 5 questions total for essential questions. But today, we are just looking at how we know if we have vertical asymptotes using calculus and using limits. So then, before we get started, you need to know a little bit about how to work with infinity because you're going to see it a lot more. And so just like we learned how to add, subtract, multiply, and divide with limits, that we could basically do those a piece at a time, we need to learn how to add, subtract, and multiply with infinity. So these first few, here, here, and here, should make pretty good sense to you. If I take infinity and I multiply it by 5, I'm still going to be at infinity because I was at the largest representation for a number that we have. Multiplying by 5 still means I'm at the largest number representation for a number that we have. And that negative is just going to flip the direction and give your answer overall as negative infinity. Similarly, if I'm at infinity and I want to add a number, infinity plus 5 doesn't make a difference. I'm still at the largest representation that we have possible. Even infinity plus a million doesn't make a difference. You are already at the largest representation possible. So then, as we take a look at these next ones, we kind of talked about this one a little bit yesterday in class. So if I take a number over plus or minus infinity, let's talk about then like just 1, for example, is really easy. And then let's deal with plus or minus 1, and then let's put a comma and a bunch of zeros. And then we could just put like a dot, dot, dot to keep going and going and going. Well, if you think through 1 over, like I have here, a million, 1 over a billion, 1 over a trillion, that gets tiny. That's 0.000000, and so on until you get to 1. So that approaches 0. So basically, 1 over plus or minus something that's really big approaches 0, something that's really small. Then, as I take a look at these next 2 over here, the direction matters a little bit more. We'll take a look at the positive example first. 1 over 0 from the right. So 0 from the right is like 0.0000. You could do a dot, 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 0, 1. Okay? So if I have 1 over 0.0000 dot, 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 0, 1, well, that's really 1 over, that being a decimal means I really have 1 over a fraction. So like 1 over 0.01 is 1 over 100th. Well, this is 1 over 1 and then a lot of zeros. 0, dot, 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 and then we had 4 more zeros is how we represented that. Well, if I am dividing by a fraction, that means I am multiplying, oops, sorry, I wanted to change that to multiplication. I am multiplying by its reciprocal. I will flip this part over. So 1 with all those zeros over 1. So then I just made a really large number. So what we learned from these two examples is that if I have 1 over something that is really small, close to 0, that is going to approach something that's really large, but I could get infinity or I could get negative infinity, depending on whether I was doing 0 from the right or whether I was doing 0 from the left. Okay. This next box, actually the next couple boxes, will come up several times throughout the class. So we've started to learn about some indeterminate forms. 0 over 0 we've already seen a lot of. And then I gave you a heads up with special trig to watch out for 0 times infinity, that comes up sometimes. Some other ones of interest, infinity over infinity, will start to come up in this section. And then these are just some other things that we can't do. Indeterminate means cannot determine an answer. Then down below it, these are items that we do know the answer to, like infinity plus infinity, we know that answer. But infinity minus infinity, that's not actually 0. We can talk more about that at another time. But these are just some boxes of information of things that we cannot, in determinate forms, can't determine an answer, have to do more work. And then things that we can, down below, determine an answer. Okay, so calculus definition of a vertical asymptote. I have a vertical asymptote, a VA, at x equals c if, well, it turns out that I need to approach c, but I need to do it from the left, and I need to do it from the right. And as I'm approaching C, my function is either going to shoot way up or my function is going to shoot way down. That's the calculus limit definition of a vertical asymptote. And it matches up with what you're used to seeing as far as how a graph behaves around a vertical asymptote. They either go way up or way down. We'll make some notes about if we are plugging in with limits. Sorry for my dog there. If we are plugging in with limits, we could get different options. We've already seen some of them. We get 0 over 0 a lot, and that means indeterminate form. That means do more work. We saw that in 1.3's analytically notes and homework. What we're going to start to see today is if I get a number over 0 or if I get 0 over a number. We talked briefly about this. 0 over a number is 0. 0 over 1, 0 over 5, 0 over negative 50, that is 0. But a number over 0, that on your calculator will say that you have an error. What it really means, if I have a number on top and 0 on the bottom, it means my graph has a vertical asymptote. And that means that my limit answer is either infinity or negative infinity, because I just learned that by definition with limits, this is what has to happen if I have a vertical asymptote. If I have a vertical asymptote, then as I approach that vertical asymptote, my function better approach infinity or negative infinity. Better shoot way up or it better shoot way down. Okay? When we actually plug in, here's how we're going to tell. So 0 over 0 means lots of different things. I don't know the answer yet. I've got to do more work. But a number over 0 means I have a vertical asymptote. Okay, we already saw the information in this next box in our topic 1 notes. So we saw in topic 1 that sometimes my function shoots way up or way down, and we will say that the limit is equal to plus or minus infinity. However, it still means that the limit does not exist. So you can have the limit of a function as an answer being infinity or negative infinity, but this still means that the limit doesn't exist. And we talked about it's kind of nice to give a clarification and list both of those options. Say, hey, this one goes to infinity or this one goes to negative infinity, but then also in parentheses put, but we know that means it doesn't exist because you can see it either way for AP. So this is just a reminder of that because you're going to see it a lot today. Okay, so for homework for sure, and like quizzes and tests, I expect you to tell me that it goes to infinity or negative infinity. And then underneath, you are always welcome to say, hey, I know that means it doesn't exist. Okay, find the limit if it exists. X needs to approach 2 from the right. Well, our strategy for finding limits is first, just try to plug in the number and see if we're okay, see what we get. So 2 from the right doesn't really matter to me right now. I'm just going to plug in 2 and see what I get. So I plug in 2, I get 8 on the top, and I get square root of 4 minus 4. I get 0 on the bottom, 8 over 0. Well, that's a number over 0. That was not 0 over 0. So 0 over 0 means to do more work. 8 over 0 means a VA. Well, if I've decided that I know I have a vertical asymptote, then what that means is because it's a vertical asymptote, it means my limit answer is infinity or negative infinity. Has to be one of those two choices. So, if I know it's only between those two, so we can just check a close number to decide, and really all we're deciding is whether it's positive infinity or whether it's negative infinity. Okay? So now let's go back to this idea that it was really 2 plus. So we could think about something that's really close on a table, 2.001. Okay? So I would have 2.001 and I would cube it. And then I would have the square root of 2.001 and I'd have to square that and then take away 4. Again, without a calculator. I don't really expect you to tell me what this decimal is. I want to know if it's positive or if it's negative. Because since I know it's a vertical asymptote, I already know my answer. It's either positive infinity or negative infinity. I just have to choose whether it's a plus or whether it's a minus. So 2.001 cubed, that's positive. On the bottom, 2.001 squared, just decide, is that bigger than 4 or smaller than 4? Well, this is a little bigger than 2, so when I square it, it's a little bigger than 4. When I take away 4, I still have a positive number, and the square root of a positive number is positive. So overall, this is positive. So if that is positive, then that means my answer is going to be positive infinity. I knew it was infinity because it was a VA. Then I know that it's positive infinity because I checked a close number. So without knowing what the graph looks like, without having a calculator, I can come down here and say the limit as x goes to 2 from the right of x cubed over the square root of x squared minus 4. That limit is equal to infinity. And then underneath, I will comment that that still means the limit does not exist because that just gives some good clarifying information. Okay. If you wanted to graph, you are welcome for right now to just confirm and check. You could check on a graphing calculator. But for AP, this would be a no calculator question. So some things we could check just by hand on a graph if we wanted to. Graphing, I would try to take a look at the denominator for VAs. Because if I have to solve with algebra, if you remember, we would always take a look at the denominators. So if I just took a look at x squared minus 4, just inside that radical, set it equal to 0, that means x squared is 4, square root both sides, x is plus and minus 2. What I should notice is that, so I would have vertical asymptotes at 2 and negative 2. You can check and confirm on your graphing calculator, but we just found when we were larger than 2, when we came 2 from the right, that we were going to infinity. So we've just figured out it's curving up like that. If you check on your calculator, you will actually see it's one that kind of has a slant asymptote. And it actually doesn't have anything in the middle. And this is something good to talk about because you should be able to decide that without a graphing calculator. It has nothing in the middle because we would end up with i's in between. So i's for x between negative 2 and 2. And you can check that by thinking through, if you come back up here, if you pick like 0, 0 squared is 0. 0 minus 4, that means that's a negative. I actually get negative values in that radical for any numbers that are 0 over to 2 and 0 over to negative 2. So that graph would just be empty. Sometimes you do need to know some graphical information without a graphing calculator. And we have found, by the work we just did, we found this information. We would know where the asymptotes were, and we checked a number and found that 2 from the right, I was going to infinity. Okay, that's just some extra stuff. Comes in handy on homework here and there. All right, here's another limit. I'm going to 5 from the left. So let's try first to just plug in 5. It doesn't really matter right or left unless I run into a problem. So I get 5 on the top. When I square 5, I get 25. Well, 25 minus 25 means I now have 5 on top but 0 on the bottom. That means I have a VA. Anytime I get a number over 0, that means I have a VA. And that means my limit answer is infinity or negative infinity. Well, then if I've narrowed it down to just those two possibilities, then I'm going to check numbers close to 5 from the left to decide whether it's going to be positive or whether it's going to be negative. But by having a number over 0, I already know it's going to be infinity or negative infinity. So that's why then I can just check like one number that's real close and just decide, is it positive or is it negative. So close to 5 from the left, we're thinking 4.99. Or maybe even 4.999. I mean, it's up to you how far you want to carry it out. But as we do that, so I have 4.99 there. Then I have 4.99, and I'm supposed to square it, and then I'm taking off 25. Well, the top is clearly positive. On the bottom, I don't really want you to square 4.99. I just want you to decide, is it bigger than 25, or is it smaller than 25? Well, this was already smaller than 5, so when I square it, it's smaller than 25. If I then subtract 25, I get a negative. So a positive over a negative is a negative. So that tells me that my answer, since I already knew it was infinity or negative infinity, now I have decided it's negative infinity. Okay, so the limit as x goes to 5 from the left of x over x squared minus 25 is negative infinity. You can also clarify that still means the limit does not exist, because we never know how we're going to see it for AP. What we've just shown ourselves without drawing out the full graph, this again has two vertical asymptotes, because if you solve the bottom, x squared would equal 25, and then x would be plus or minus 5, but we have figured out there's a vertical asymptote at 5, and we have figured out that as we approach it from the left, our graph is shooting way down. you could graph the full thing on your graphing calculator or spend a little while longer messing with it by hand. But this is what our quick analysis to answer this limit has shown us. Okay, so some things to pay attention to. I really didn't care that it was 2 from the right or that it was 5 from the left until I started to plug in and realized I had a problem. I got a number over 0, and that meant it was kind of a weird case. It was a vertical asymptote. Then I needed to know which side I was coming from so I could decide if the limit would go to positive infinity or negative infinity. But overall, our first step on limits is still to plug in the number. Whether it's one-sided limit or not, our strategy is always to first plug in the number. Okay? If it works out for you, then just move on and give an answer. If it turns out to be 0 over 0, try some strategies we learned earlier. If it turns out to be a number over 0, then that's where today's section's coming in. Okay, now I want the limit as I go to pi over 2 of tangent of x. There are 2 ways to do this, and it depends on how you best work with trig. So way 1, it is fair game to know any of the 6 trig function graphs. We can usually get around it if we're good with our unit circle, but if you already know all of your 6 trig function graphs, then you could do it by trig graphs. So if you knew that, we're only interested in pi over 2. Trig for tangent of x actually has asymptotes at pi over 2 and at negative pi over 2. It goes through 0, 0, and it curves up kind of like this. Then you have your next asymptote at 3 pi over 2, and it curves like this. It's a periodic function. It just keeps repeating and repeating and repeating. I'm not real concerned with all those intercepts because I'm really only interested as x goes to pi over 2. So as x goes to pi over 2, from the left it goes up, from the right it goes down. It's not a problem that they're going to infinity, but it is a problem that it's not doing the same thing on the right and the left. So I can't answer this question as far as a limit existing. This limit does not exist because the sides are not equal from the right and the left. Okay, well, another approach, if you don't want to memorize or you don't have memorized all 6 trig function graphs, then another way is the unit circle, which there's no real way around. We all need to know the unit circle. So let me show you this approach if you don't think you're so great with all of the 6 graphs. Let's change to sines and cosines. So the limit as x goes to pi over 2 of sine of x over cosine of x, and think about it as a ratio. And if I just straight plug in pi over 2 is up here in the unit circle, that has a coordinate of 0, 1. Sine is the second coordinate, so sine is 1, cosine is 0. So that right there can tell me that I'm going to end up with a VA. So I know that it's going to be positive infinity, or I know it's going to be negative infinity. And then if I just want to decide which one, if I'm just trying to decide between the plus and between the minus, then let's take a look at a unit circle approach to help with that. So let's draw a bigger unit circle. And I'll kind of mark this in some different colors. So if I wanted to look at this portion, so here's my, oops, sorry, let me mark. Here's my pi over 2, like we talked about. It's up there at the top. But then if I want to approach from the left and from the right, so for this portion, as I'm coming up this way and I'm really, really close, like right, sorry, I'm not the best with this pen right now. As I'm really close, like right here, I'm approaching and I'm in this area really, really close. This would be approaching pi over 2 coming up this way, goes to pi over 2 from the left side because you're coming from smaller numbers than pi over 2. Well, in that quadrant, everything in this quadrant has 2 positive signs. So if I make a ratio of sine and cosine, both of those coordinates are positive, so my tangent ratios are positive. So I can tell that on the left side, when I am smaller than pi over 2, my tangent ratios are positive. And if I go look at my graph, I see that. Well, then if I want to switch over and I want to look as I'm coming past and working my way around the unit circle, so like right here, this would be as I am approaching pi over 2 from the right, because I am now larger than pi over 2, and from the right means bigger numbers. In this entire quadrant, the coordinates are negative and then positive. So as I approach pi over 2 from the right, my tangent ratios, doing sine over cosine, my tangent ratios in quadrant 2 are negative. And I can see that back over here on the graph, that when I was bigger than pi over 2, when I was on the right side of pi over 2 on the graph, my graph was pointing down. So I can see from the graph that one side goes up and one side goes down, and I can also see on the unit circle approach, from one side when I was smaller than pi over 2, I got positive ratios, but once I passed it and I was larger than pi over 2, I got negative ratios. So either approach doesn't make a difference to me at all which one is easier for you, but from either approach, the limit as x goes to pi over 2 of tangent of x does not exist. I could do one-sided limits and clarify whether they are infinity or negative infinity. But overall, limit does not exist, because if you have to explain, the limit as x goes to pi over 2 from the left of tangent of x did not equal the limit as x went to pi over 2 from the right of tangent of x. I'm not going to box all of that because I have a lot of boxing going on, but this is your answer for this question. And if I asked you for support, I would take either option as far as support. AP is not going to ask you to explain something as basic as just a trig function. They're going to expect that you know those kinds of things. So you don't have to worry about having like the nicest AP quality work on something like that. If you are struggling with the unit circle, make sure that you start practicing. Find some online quizzes that'll see what you remember, fill in some blank ones, whatever that takes. You've got to know your unit circle. Okay, now we're going to switch over to some questions that just ask us to find vertical asymptotes algebraically. Hang on for one. All right, so if you have to find vertical asymptotes with algebra, this is a review of what you did in Algebra 2 and Math Analysis. We cancel anything that's in common first, and that canceling gives us a whole. We will see early next week that is called a removable discontinuity. Then you look at what's remaining, and from what's remaining, you have a vertical asymptote when you have a number over 0, not when you have 0 over 0. If you have a number over 0, that means that your limit answer is infinity or negative infinity. And if you have 0 over 0, remember that means that you need to do more work. But so what you're used to from Algebra 2 Math Analysis is that to find VAs, you first factor and cancel. Whatever you cancel makes a whole. Whatever is left, you look at where the bottom is 0. But you have to make sure, now that we know all these tricky cases, you have to make sure it's only the bottom that's 0 and not top and bottom that's 0. Okay, this next example I'm going to skip for the sake of time. There's a lot in day 1 and this is pretty easy. Let's go to next page, number 5. Okay, find the vertical asymptotes, if any. And we're starting with secant of pi x, and they want us to go around the unit circle one time. Okay, so f of x equals, and let's go back to sines and cosines. That is 1 over cosine of pi x. and I have a VA whenever I have 0 on the bottom, but I want to check that I don't have 0 over 0. Well, it's just kind of nice to make a mental note that 0 over 0 is impossible here because you have a 1 on top. That 1 is never going to change to become a 0. So 0 over 0 is just not even a case we have to worry about here. So I now know that I have VAs whenever the bottom is 0. So that would be whenever cosine of pi x is equal to 0. Well, we're going to make a substitution to help us deal with this pi, with this stretching and shrinking sort of idea. So we're going to let theta, because we're dealing with trig, so a common substitution would be theta. Let theta be pi x. So then we're really just going to try to solve when cosine of theta equals 0. And we're just going to think about that on our unit circle. Cosine is our first coordinate, the x coordinate. The x coordinate is 0 when I'm up here at pi over 2 and when I'm down here at 3 pi over 2. So whenever theta is pi over 2 or 3 pi over 2, and that just keeps going and going and going, so I'm going to put a dot, dot, dot. I could cycle around the unit circle as many times as I want, and every time I hit those top and bottom pieces, I end up with cosine being 0. I'm actually going to put a dot, dot, dot to the left of pi over 2 because really I could read the unit circle clockwise if I want to, and have negative pi over 2 and negative 3 pi over 2 as far as angles. This is where your interval comes into play. They only wanted us to go around the unit circle one time, and they wanted us to go in the positive, so in this case, counterclockwise direction. All right, well, my original question dealt with x's, and now I have this theta. I need to go ahead and send it back so I can end up with x's. So remember, theta was equal to pi x. So instead of theta, I'm going to write pi x is equal to, and then I have this information, dot, 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 pi over 2, 3 pi over 2, and so on. Okay, I algebraically need to get rid of that pi that's right there because I need to know just what x is. So I divide by pi there. That means I also divide by pi here. I divide by pi here. And I would keep dividing for all those different options. So that means x is equal to, could go on in the left direction, 1/2, then 3/2, could go on in the right direction forever and ever and ever. But x was supposed to be only from 0 to 2 pi. Well, that's kind of hard. I mean, I really have to think at least a little bit because I got rid of all my pi's, so I just have 1/2, 3/2, and so on. I for sure don't need any negatives because it started at 0 and went on. I just need to know that 2 pi is approximately, well, 1 pi is approximately 3.14, so 2 pi is approximately 6.28. So how long would I have to continue this? So I am going to say that I have VAs here whenever x is equal to 1/2, 3/2, 5/2 would be the next one. And then if you have 3 things in a row that are making a sequence like that, you can just put a dot, dot, dot in the middle to continue the pattern. But you've got to tell us where that pattern stops. So 1, 3, 5, 7, 9, 11, 13, so on and so on and so on. When do you get to be too big? You've passed 6.28. So I need to think to myself that 13/2 is 6.5. Well, that's already too big. So I need to go just up until I would hit 13/2 and stay underneath it. So I would stop at 11/2. 1, 3, 5, 7, 9, 11/2. Oops, that kind of ran into my dot, dot, dots. Okay. This next question is again with trig. Tangent theta over theta, and I want to find any vertical asymptotes. All right, if I'm dealing with vertical asymptotes, let's go to sines and cosines. So g of theta is equal to sine of theta over cosine of theta. But then I had this theta that was already in the problem in the denominator. So I'm going to put it in front because we'll typically do that. The little pieces we'll put in front. Okay, so for a VA, I want to consider when theta times cosine of theta is equal to 0. But I will also have to check to make sure that I don't have 0 over 0. So actually, before I write that, let's check to make sure I don't get 0 over 0. Because remember, that did not tell me that I had a vertical asymptote. 0 over 0 just told me that I had more work. So I'll first start by setting the bottom to 0 because nothing's going to cancel here. So I'll start by setting the bottom to 0, but then I have to go back and think about if I end up with 0 over 0. Okay, theta times cosine of theta being 0. This is multiplied together, so we can solve by factoring. We can split it apart. This means that theta is 0, or this means that cosine of theta is 0. We just solved up above when cosine of theta is 0, and if you go back and check our interval, they want 0 to 2 pi, so just one time around the unit circle. So pi over 2 and 3 pi over 2. And theta is pi over 2 and 3 pi over 2. Okay, so that means that these are my candidates. Candidates for VAs. You need to check, do they cause 0 over 0? Do they cause you to get 0 over 0? If so, remove them. They are not VAs. I only have a VA if I end up with a number over 0. So basically, you can just go and check and plug in. So I can go back up to the fact that g of theta is equal to sine of theta over theta cosine of theta. And I can just check, what is g of 0? Well, sine of 0 is 0. And then theta on the bottom being 0 times cosine of 0 is 1. This is a problem. I get 0 over 0. That means theta equals 0 is not a VA because I got 0 over 0. Whenever you run out of room, there's a lot more room for this question on the next page, so feel free to turn over. Then I also need to check pi over 2 and 3 pi over 2. But they're going to behave similarly because they have the same x coordinate on the unit circle. It's just the y is going to switch between 1 and -1. So really, I can plug in each one of them, or I can just think about, so if I want to check g of pi over 2, sine at pi over 2 is 1. Then I would have the pi over 2 on the bottom, and then cosine at pi over 2 is 0. So that is a number over 0. That is a VA. All that's going to change when I go up and put the 3 pi over 2 is that sine of 3 pi over 2 is -1. That's still a number over 0. That's still a VA. So you're just cycling through, and these checks could even be in your head. It's not a problem. You don't really have to write it down. But before you decide what your VAs are, you need to go through and check that they don't cause 0 over 0. So my final answers for where I have VAs, I only have VAs when theta is pi over 2 or 3 pi over 2. Okay? I'm going to go to the next page now just because I'm definitely out of room, and if I keep scrolling down, it just gets harder to read. Okay. So process for VAs is figure out where the denominator is 0. We did that in both of these last two examples. But then also make sure that you don't get 0 over 0. Well, I couldn't have in this top example because I had a 1 on top. But in this next example, I had a sine function on top, and sine is 0 sometimes. So I have to check and think through when sine is 0. That option is not a VA. So my final vertical asymptotes are just pi over 2 and 3 pi over 2. Okay, this next part, the B and C part are just finding limits, and just to reiterate to you like what a VA looks like and what it doesn't look like. I want to skip that for right now and just do these last two limit examples and see where we're at for time. Actually, let's see where we're at for time right now. Okay, you're kind of close. So if you were running out of time in class for these, they are posted online, and this is just really at this point, this whole last page is extra practice. But let's go through 7 and 8. Okay, so I have x approaching 0, and then I want it of 1 plus 1 over x squared. Well, as I go through that, if I just start plugging in, I would get that that's 1 plus 1 over 0 squared. We talked at the beginning today, 1 over something that's really, really tiny is really, really big, because you have 0.00000001 on the bottom, and that decimal on the bottom really means you had a fraction on the bottom, which flipped it up to be really, really big. So this approaches infinity. So it turns into 1 plus infinity. And we talked at the very beginning, adding 1 to infinity doesn't change the fact that you're still at infinity. We can clarify, that means this limit doesn't exist, but we're going to be specific and give what information we know. This is also a time it might be nice for you to just go back and say, oh, that 1 over x, that 1 over x squared, that's a graph I know. That's the one that was in quadrants 1 and 2. And then you could take a look as you approach 0. You can see both times if you approach 0 from the left and the right, you approach infinity. So you could do a graphical approach or you could plug in. This is a case notice. The reason I just kind of sprinkled these in, I didn't get a vertical asymptote answer out necessarily for the whole thing. I got the one part first, and then I had the number over 0 part for the second part. Okay, now limit as x is going to -3, but from the left. Well, let's first just think about -3. And I could plug in as is, or if I think it's easy to factor, I could factor to see if anything would cancel. So I get limit as x goes to -3 from the left. This does factor. You'd end up with x plus 3 and x minus 1 on top. And you'd end up with x plus 3 and x minus 2 on the bottom. So in this case, it does cancel. Even if it doesn't, factoring is sometimes a good mental math strategy because it's easy to plug in the -3 when you have just little pieces to plug it into. But this cancels, and then now I can come back and say, okay, I'm going to plug in the -3 part. We don't even need to worry about this minus from the left right now. Let's just plug in and see what we get. We'd get -4 on top, and then -3 minus 2, we get -5 on the bottom. It doesn't even matter that I was approaching from the left because I didn't get any kind of weird answer. I was just able to plug in and get a normal answer, so 4/5. This didn't involve a vertical asymptote or infinity at all. So sometimes you're just going to see random normal limits sprinkled in. You're probably getting close to time class-wise, and that's okay. I am going to go back and finish up the limit examples right here, and then we skipped one of the examples about finding a vertical asymptote with just algebra. So I'll show those so that our Schoology notes are completely full if you're wanting extra practice. But if you only got this far in class, you know plenty to be able to do your whole assignment for homework 1. Okay. All right, so if we want to go back to this example, we already figured out where we had vertical asymptotes. We figured out that in one of our cases, it actually wasn't a vertical asymptote because it caused 0 over 0. And then we figured out the other two were. So now if I want to find these limits, we're just going to kind of make some connections there. So to do part B, I want the limit as theta is going to 0. And I'm going to do sines and cosines. So sine theta over theta cosine theta. Okay, Hopefully, the sine theta over theta is looking really familiar to you. That's one of our special trig limits, and that limit goes to 1. So this portion turns into 1, sorry, I would write it probably as the 1 that we figured out from the special trig limit, and then times this other part that's left, so that would be 1 over cosine of 0, but cosine of 0 is 1, so my overall final answer would be 1. Okay, this illustrates to us, again, remember we found when we were finding vertical asymptotes that theta equals 0 was not a VA because we got 0 over 0. When we checked it, we said, oh, okay, that means it's not a VA. Well, yeah, this is showing us this is not a vertical asymptote answer. Because a limit, if I'm seeing a vertical asymptote, my limit should be infinity or negative infinity. So this is just kind of making that connection and confirming it. That if all you do to find vertical asymptotes is set the bottom equal to 0, sometimes you're going to get some things that aren't vertical asymptotes. If you checked through the limits, that would also be another thing you could check, or just checking that you don't get 0 over 0. Okay, for part C, let's look at the limit as I go to pi over 2. Now, if you remember, that was a vertical asymptote, so our limit should be infinity or negative infinity. Okay, and as we take a look at that, now sine theta over theta does not go to 1 because that only happens if I was approaching 0 or if I was approaching plus or minus infinity. When I approach pi over 2, I can just plug in. I can find the sine of pi over 2 and the sine of pi over 2. Think through your unit circle. It's 1. Then when I plug in theta, that is pi over 2. And then when I plug in cosine at pi over 2, cosine at pi over 2 is 0. So now I'm seeing a number over 0. That is a vertical asymptote case. That means infinity or negative infinity for my limit answer. And if you notice, this is confirming we already knew it was a VA. So we saw it was a VA in part A when we did it. So this is just kind of confirming. Technically, if you go back to the example on the top of 2 pages ago, we saw the graph for tangent of x like that, and so we know that we're not going to get an answer because one side's going to go up and one side's going to go down. So as theta goes to pi over 2, that tangent of x part, that limit does not exist. So tangent theta over theta does not exist if we're trying to just answer the limit question. But really, those limit questions are there to kind of confirm for us, hey, on the last pages, these were both candidates for vertical asymptotes, but only the pi over 2 ended up being that because only the pi over 2 and the 3 pi over 2 was giving us a number over 0. The 0 case was giving us 0 over 0, and if I work out the limit, I get an actual numerical value, not infinity or negative infinity. So that's just another illustration of how vertical asymptotes work with limits. And now if you want to backtrack to do the algebra example that we skipped, this one, this is just a good example to remind you of factoring and canceling. So it's not a huge deal, but we can go through it so you have it to see. So g of x, on top, what's in common? Well, there's a 4x. Take it out, I get x squared plus 6x plus 9. On bottom, this is a little bit of that weird factoring. You don't want that 1/3 there because you can't really tell what you're working with. So if I take out a 1/3, I'm dividing by it because I pulled it in front. That really means I'm multiplying by 3 to figure out what's left in there. So I would get x squared plus 6x plus 9 when I multiply all those coefficients by 3. The 1/3, the 2, and the 3. Well, that entire parenthesis term wipes out. When that wipes out, that means you have a hole, and technically you have a hole. If you were to factor this more, it's really x plus 3, x plus 3. So you have a hole at x equals negative 3. And then as you keep going, you have 4x over 1/3. Dividing by 1/3 is the same as multiplying by 3. So you have 12x. 12x doesn't have any more, well, it has a 1 in the denominator, but it doesn't have any variables in the denominator. So there are no VAs because that's where I look to determine vertical asymptotes. I did have a hole. That wasn't what this question was asking, but I did have a hole, but I didn't have any vertical asymptotes. Okay, so that finishes everything, every last detail of every example, if you're wanting to go through everything and have some extra practice. Remember that you can rewatch, fast forward, pause, do whatever you need to on this, if it helps you as you're piecing together homework and everything. Thanks.